DOE CSGF Fellow Daniel Jacobson in the field of computational chemistry at the California Institute of Technology.
My name is Daniel Jacobson, and I'm in the Miller Group at Caltech, and the title of my talk is the Dendritic Transition in Electrodeposition, the Reaction-Diffusion Length. So if we want to deal with climate change, we are going to need to switch over to electric cars at a large scale. And one of the current limiting factors with designing effective electric cars is the performance of batteries. And so we'd like to design better batteries. Now, quickly, let's review how batteries work. Batteries have three components. There's an anode, an electrolyte, and a cathode. And ions flow back and forth from the cathode to the anode during the operation of the battery. And electrodeposition occurs inside the battery at the surface of the anode and at the surface of the cathode, where the ions plate onto the anode and the cathode. And if we want to build more effective batteries, more energy-dense batteries, we can swap out the anode and cathode materials for better materials. And one of the materials that's looked at a lot for swapping out the anode is to use lithium metal as a next generation anode. It's very energy dense. But the problem is that when the lithium ions plate onto the lithium metal anode, they don't plate nice and flat. Instead, they form these irregular branching structures called dendrites. So over here, we have an optical microscopy picture of dendrites that have formed on a lithium surface during electrodeposition. These dendrites form on the surface and they create all sorts of problems inside the battery. And so at a high level, we'd like to understand why does dendrite formation occur in this context. Now, that's a complicated question that many people are attacking from many different ways. But the way in which I approach this question is through the study of very simple models. So I study a very simple Brownian Dynamics model that models electrochemistry. And the way it works is you start out with a cluster. In this case, it's just one particle, and that particle's frozen. The cluster's frozen. And then you release a free particle, a free Brownian particle far away. And that Brownian particle diffuses. And eventually, that Brownian particle comes into contact with the cluster. And when it does so, there's a chemical reaction that drives the free particle to stick to the cluster, and it joins the cluster and becomes part of the cluster itself. And you just repeat that process over and over again. And you can build up a cluster that looks like this. So this is actually an interesting example of a very simple non-equilibrium deposition process. And it is a very simple model of the ions plating onto the anode in an electrochemical device like a battery. And so this model just has one parameter, which is the dimensionless rate constant, which just characterizes the speed at which the free particle reacts with the cluster when it comes into contact. And now this is composed of the K, which is just the rate constant, A, which is the particle size, and divided by the square root of D, which is the particle diffusivity. And so this dimensionless rate constant controls how quickly the free particle sticks to the cluster. And you can roughly think about that as the probability that the free particle sticks to the cluster upon making contact is proportional to this dimensionless rate constant. Interestingly, it's actually also proportional to the square root of the time step. So the probability of sticking is not actually a physically well-defined quantity because it's proportional to the time step. So the definition of this model is a little bit subtle, but roughly you can think of this rate constant determines how sticky the cluster is. So when the rate constant is very large, when the reaction is very fast, the cluster is very sticky, and the ion or the free particle is very likely to stick to the cluster upon contact. Okay, so now that we have this very simple model of the behavior of this non-equilibrium deposition process, we can see what this model does. And so we just start to run the model and build up a large cluster. This is at a specific value of the dimensionless rate constant up here. And this is 50,000 particles. And we see we get a nice compact cluster with rough edges. This is not too surprising. The bands of color here represent 1/5 the total number of particles, so 10,000 particles in each band. Now, that doesn't look too surprising, but as we continue to plate, suddenly we get a transition from something that looked compact into something that has this branching fractal structure. So this is 2.5 million particles, and you can see that this very clear split has happened between this compact structure in the middle and this sort of larger fractal structure. So this model, even though it's so simple, displays a transition from a compact morphology to a dendritic morphology. And the branches of this structure look like, roughly like, these sorts of optical microscopy images that we saw of lithium metal dendrites. So this transition happens at a characteristic critical radius. You can just see it visually that when the cluster gets to be about this big, about the size of this guy over here on the left, it splits into this fractal shape. And so not only does it split into a fractal shape, but sort of the critical radius, the point at which it splits into a fractal shape, depends on how sticky the cluster is. So for example, these two clusters both have the same number of particles in them. They both have 2.5 million particles. But this cluster over here was run at a much smaller value of the rate constant, so it's much less sticky. And so even with 2.5 million particles, this cluster has not split into the fractal shape yet, that this one has split. So roughly, the critical radius goes up as the rate constant goes down. When I move from a larger dimensionless rate constant to a smaller dimensionless rate constant, the radius at which I split into a fractal increases. And so roughly, the critical radius is a function of the stickiness or the dimensionless rate constant. Okay, so that's how this model behaves. And we'd like to know if this model can help us explain dendrite formation in batteries. But the question we need to answer before we talk about that is just what actual mechanism causes this transition within the model? Why do the ions move from why do the free particles move from plating onto a compact structure to suddenly forming this fractal structure at the critical radius? So this is sort of the main question that's going to motivate the rest of the talk. Why does this split within the model occur? Now, the last thing we have to talk about is we have to talk about characterizing this transition from being compact to being dendritic. We have to characterize that quantitatively. We've sort of talked about things visually so far, but we're going to need to test out quantitative hypotheses. So the first thing we have to do is we have to define a characteristic radius for the cluster. And we can do that by just using the radius of gyration, which is just the root mean square radius of all the particles in the cluster. And then we need to define an observable that will actually track the transition from a compact to a dendritic structure. And we can do that using this quantity called the fractal dimension, which is defined as the derivative of the log of the number of particles in the cluster divided by the log of the radius, or with respect to the log of the radius of gyration. And the details aren't too important here. The point is just that if the structure is compact, the fractal dimension will be 2. This is in 2 dimensions. And if it's not compact, if it splits into that fractal branching structure, the fractal dimension will be less than 2. And so sure enough, if we actually do this, we see that this works. So this is a plot of the fractal dimension on the y-axis and the cluster radius on the x-axis for various values of the stickiness of the dimensionless rate constant. And we can see, for example, for this blue curve, which is a very non-sticky cluster, the fractal dimension is initially 2, so this cluster is initially compact, and then eventually at some point the fractal dimension starts to drop. And so it splits into this fractal shape. And we can see that the larger the rate constant, the less sticky the cluster, the sooner that drop, that split between a compact and a fractal shape occurs. Now, interestingly, the fractal morphology seems to plateau at about 1.71, regardless of the value of the stickiness constant. And that's an interesting feature of this model, but it's not one that I'm going to focus on in this talk. So the last thing we need to do is we need to characterize the critical radius. Sort of before, we were just talking about the critical radius as being a value or as being something you can see visually, but we want to characterize it quantitatively. And so we can define the critical radius to be the steepest point, the steepest slope on this curve. So the critical radius, the point that separates the transition from compact to fractal, is just the steepest point on this curve. So somewhere around right here on the green curve. Okay, now that we understand these things, we can propose a mechanism for how this split is occurring. And the mechanism that we propose is sort of revisiting an older mechanism, although that mechanism was sort of phrased in terms of sticking probabilities, which aren't actually physically well-defined quantities. So it's a little bit confusing, but the mechanism is roughly the same. And that mechanism is just that there's a parameter called the reaction-diffusion length. And that reaction-diffusion length is the square root of d divided by kappa, the rate constant. And d is the diffusion constant. And so the details I don't want to go into too much, but really this thing is pretty intuitive. It's just the length the particle can diffuse within the characteristic reaction time. So there's a reaction at the surface of that cluster that drives the free particles to stick to the cluster. And that reaction has a characteristic time scale. And within that time scale, the ion or the free particle can diffuse a certain length. And that length is the reaction diffusion length. So we have this reaction diffusion length parameter. And if the cluster radius is smaller than that reaction diffusion length, that means when the particle comes in to see the cluster like this, it's going to be able to diffuse around that cluster pretty easily without worrying about sticking. And when it's able to diffuse around the cluster easily, it actually equilibrates with the cluster geometry and sort of becomes equally likely to explore all the valleys and the tips on the cluster and becomes equally likely to stick anywhere. And when it's equally likely to stick anywhere, that leads to nice compact growth. But as the cluster grows, eventually it becomes larger than the reaction diffusion length. And when the cluster is larger than the reaction diffusion length, suddenly the incoming particle can't explore the entire cluster anymore. Suddenly it sort of comes in and it sees the tips and it doesn't really have time to explore all the valleys first. And because the tips are the first thing it sees, it's more likely to stick on the tips. And then once it sticks on the tips get bigger, and then the next particle becomes even more likely to stick on the tips. And that sort of feedback loop is ultimately what leads to the splitting of this compact structure into something that looks branching and fractal. So we propose this mechanism in a pretty qualitative manner, but we want to test it quantitatively to ensure that this mechanism is actually right. And so how we can test this quantitatively is we can look at taking the continuum limit. So what we proposed here is that the critical radius is proportional to the reaction diffusion length. Now, the only other option is that the critical radius would be proportional to this type of power law form. And this just follows from dimensional analysis. This thing over here is a length. So these two guys, which are the only two lengths in the system, just have to form a product such that their power gives units of length. So eta and 1 minus eta. Eta is a generic exponent. And eta could be different than 0. And basically what we proposed is that eta equals 0. So we're trying to distinguish between eta equals 0 and eta is not equal to 0, which would be the more generic form. And the way we can do that is by thinking about taking the continuum limit. So when we take the continuum limit, we take the particle size to 0. And when we do that, because this guy does not have a dependence on the particle size, then we expect the critical radius here to go to a constant. But since this guy, a constant that's non-zero, but since this guy does have a dependence on the particle size, if eta is positive or negative, depending, the critical radius, when we take a to 0, will either go to 0 or it will diverge. And so if we take the continuum limit and our critical radius does not diverge, then we can be pretty sure that our proposed mechanism is correct, or if our critical radius does not diverge or go to 0. So we predict that as we take the continuum limit, the critical radius is going to go to a constant greater than 0. That's the prediction. And now, because A appears in the definition of the stickiness parameter, or the dimensionless rate constant, taking A to 0 is equivalent to taking the dimensionless rate constant to 0. So that's what we're going to check. We're going to check that when we take the dimensionless rate constant to 0, the critical radius goes to a constant greater than 0. And if that is true, that's going to confirm our proposed mechanism for the reaction diffusion length. All right, so these are the results when you run large simulations. So again, I have a plot of the fractal dimension on the y-axis. And on the x-axis, I have the radius of the cluster rescaled by the reaction diffusion length now for various values of the Dam-Kohler number. And you can see right away that sort of the points of the steepest slope points line up, which is a good sign. But we can be more precise than that. So we can take the points with the steepest slopes and we can plot them on a graph here. So now I'm just plotting the critical radius directly as a function of the Dam-Kohler number. And you can see that this thing is sort of showing the beginnings of a plateau as I decrease the Dam-Kohler number. So we're seeing the start of a plateau. And now this plateau doesn't look necessarily so great on this graph, but keep in mind that we've varied the stickiness parameter over 2 orders of magnitude here. And this critical radius has gone up by maybe a factor of 50%. So this is a pretty good sign that this thing is actually converging to a constant. If it is diverging, it's diverging very, very slowly. And it's pretty clear that it's not going to 0. So we can be pretty confident confident, based on this evidence, that our proposed mechanism is correct for how this system is behaving. Now, because this is computational fellowship, I have to talk about computation. And running these simulations actually takes a long time, because the smaller the stickiness parameter is, the more particles I need to actually see this fractal dimension parameter start to drop. So for example, for calculating this blue point here, I had to generate clusters that are on the order of 200 million particles, which is quite a few. Not only that, but at low stickiness values, the particle takes longer to stick to the cluster in the first place. So it takes even longer per particle, and you have to run many more particles. So actually, we've run this system out for orders of magnitude beyond what has been able to be done in the past, using very large computer simulations. And we also have a better methodology for evaluating how we do these calculations. And we've sort of been able to see a much better plateau in this critical radius parameter, giving much stronger evidence here that the reaction diffusion length mechanism is correct. And while 2D, we don't see a full plateau, we can fix that by looking at 3D. So we can run the same process in 3D. This is what the cluster looks like in 3D. It forms the same sort of branching fractal structure, but just in 3 dimensions instead of 2. And this thing has a compact core, just like 2D has a compact core. You just can't see it because it's 3D and it's being covered up by the other branches. And now if we look at the critical radius here, we see a nice plateau. So we see a really nice plateau in 3D that we sort of didn't have the computational power to get to in 2D yet. But this provides really strong evidence that in 3D, and likely in 2D as well, because you wouldn't expect it to be any different, the reaction diffusion length mechanism is correct. So the last thing I want to say is this also represents sort of a non-equilibrium phase transition like sharpening behavior, because the slope of these curves is getting steeper and steeper as the Dam-Polar number drops. So this is kind of an interesting non-equilibrium phase transition like behavior in that it's sharp. And we might think about in the future how we can classify this in terms of different non-equilibrium phenomena. And we can think about other kinds of systems where this kind of behavior might show up. So just to conclude, we've confirmed that the reaction diffusion length controls the critical radius. We can now think about how this might apply in batteries. And we expect that the critical radius is small for lithium metal. That's why we form dendrites. We get very quick crossovers from compact to dendritic to morphology, and that's why we get a lot of dendrites. And so we expect RC to be small, and we might think about why that is. And it turns out kappa is sort of a fixed thing that's set by the electrochemistry itself. So we don't expect that to vary much from material to material. But the diffusion constant might vary a lot from material to material, because lithium is actually so reactive, it forms a solid coating on its surface when it comes into contact with the electrolyte. That solid coating is called the surface electrolyte interphase. And that solid coating may have a poor diffusivity for lithium ions, and that may lead to dendrite formation. So that's all I have. Just to conclude, I'd like to thank my advisor, Tom Miller, and the Miller Group, and also say thank you to the Department of Energy and Krell. The Computational Science Graduate Fellowship has been wonderful, and I would not have been able to pursue this work in the same way without it. Thank you.